Yes, thank you for coming to the third part of the Southeast Summer Seminar Series. This time, the speaker is Thiago Fleury from IIP in Natal, and he's going to talk about ADS5 cross S5 supergravity vertex operators. So please start.
Okay, thank you very much. I start by thank you the organizers for the opportunity and for the invitation to give this talk. So the title of the talk it's ADS5 size supergravity vertex operators, and I have thank my collaborator in this program. It's Lucas Martin. He's a PhD student in São Paulo. So yeah. So the outline of my talk, I will start with some motivations and introduction. And then I will review a bit this, because I will give the expressions for these vertex operators in the pure spinor formalism. So then I will review a bit the pure spinor formalism. I will say something about general backgrounds and specifically, because I believe some of the techniques you can apply to other backgrounds as well. But then I will focus in the ADS5S5. Then I will explain the construction of vertex operators. And then in the very end, I will conclude and say mention some work in progress. So, okay, so introduction and motivation, just background, ADS5S5 is supported by a Hammond flux. So to study it, you can use the pure spinor formalism or the Green-Schwarz formalism. There are some programs to understand Hammond backgrounds with Hammond-Neveu-Schwarz formalism, and also ambit twister strings in ADS. So there are some progress. But in this talk, I will focus in the pure spinor formalism, and I have to say that the action of the pure spinor formalism in ADS5 and S5 is now for many years, like 20 years. And only now the vertex operators were constructed there are some history. So, but the action are now for many years. It appears in the first paper in the pure spinor formalism. And there are many progress. You understand this background, the strings in this background via ADS-FT. So there are many techniques, integrability, we saw also the last talk. So there are many progress to understand these backgrounds and to understand correlation functions, amplitudes, and via ADS-FT. So also in the introduction about the amplitudes, I mentioned to compute the amplitudes in this formalism, you need, of course, vertex operators that describe your states, and also it's necessary a prescription for the zero mode of this worksheet, the worksheet variables. So there is a prescription. So the vertex operators were known before only close to the boundary. That I will say just a few words of this expression close to the boundary. But also in the -8 picture, this is very new. This was like 1 year old that Berkovits constructed this vertex operator in the -8 picture and then basically I will explain more what it is during the talk. So before using this close to the boundary vertex, there was one amplitude that was possible to compute. It was basically you put some d-branes in the boundary of this the space, and this was the computation by Thales and Berkovits, and then they could compute a closed string vertex with many open string vertex, and they computed this amplitude and get what was expected by the holographic principle. So this was the only amplitude that was computed before, and because the branes are very close to the boundary, you can use and you have the open strings in this d-brane in the boundary. It was possible to use the prescription of the flat space, and they managed to compute. So here is This time we compute the bulk vertex, not only close to the boundary, but in the full space. And I just put the schematic form here. It depends. There is some integer n that measures the R chart and the conformal dimension of the state. And also there are just n is an integer. And I will explain everything, but just now it's possible to try to compute book to book amplitudes for the first time, not in general. But the prescription is still some work to do to compute these amplitudes. So okay, so I will just say a very short review about the pure spinor formalism. So because these vertex operators, the way it is constructed, it's possible it seems that we can extend to other curved backgrounds. So, okay, so very only here the notation. So if you start with some gamma matrix, like 3x3 matrix, you can always write it in the value in this basis, like the value basis. And a pure spinor, it's a bosonic spinor that satisfies these constraints. So this is basically the goal sector of this pure spinor formalism. This is why the formalism receives its name. And there are, in general, for general curved background, there is an action. Here I put type 2b, but you can put type 2a if you want. And there are here, it's a function of these curved variables. So here is my notation, the variables, and you have all the fields in supergravity. So basically this action was constructed by Berkowitz and Hoey. And basically it's very general. So you have the metric. Here is the view super viewbind that connects the curved with the tangent superspace index. Then you have the B field, then the spin connections, and the P contains all the Ramon field strengths. So the formalism works for any flux. And this S is related to the curvature. So this action is it's very general. And if you want to go for ADS5, S5, for example, you just plug the values of the background fields in the action, as I mentioned, and you get the fields. So maybe some of these techniques, the vertex operators in the -8, or solving this cohomology numerically, maybe it's possible to extend to other backgrounds in the pure spinor. So one complications to construct the action is because everything here is a superfield, and if you want to compute some theta expansion, it's very difficult. I don't know. I think it's in general it's very hard how to do this theta expansion. Only for coset backgrounds like ADS, I know, for example, to do for coset background there are some way of computing this theta expansion and get all the expressions of these superfields. But then this formalism is BST invariant. So there is a BST that has two pieces, like a left movement, right movement, and just the constraints that the BST is nilpotent, and that this charge is well defined. So just holomorphic and anti-holomorphic constraints. You see that all the superfields that appear in the action, they satisfy the supergravity equations of motion. So the superfield satisfies the supergravity constraint, only imposed that the theory is constant, like nilpotence and also holomorphism of this current. So the vertex operator. Now I'm still being general about more backgrounds. So the physical states, the physical vertex operators, are states in the cohomology of the BST operator of ghost number 2. So the vertex operators are annihilated by this BST operator, and they are not exact, and they are usually gauge superfields, because you can act some gauge transformation here, some BST exact terms. So it was shown in this paper by Berkowitz, Changia, that the vertex has this form in a general supergravity background. So what is it? It's a gauge superfield. It's just one superfield in a gauge superfield. And the way they show that this is the form is basically you know the form of the BST operator in any background, and then you show that it reduces correct to the flat space and respect all the isometries of the background. But the difficult thing is, of course, to know if you want to get the expansion of the superfield is complicated. It's just one superfield in any background. So now I will focus in ADS5S5. So the superspace is a coset, right? Coset is a super coset. And basically, as I mentioned, it's very general. If you want to get the action, for example, you plug the values of the superfields in that general action, and then you get the action for the ADS5S5 pure spinor. So then you have the Ramon flux, right? And then you have also the curvature here, the sphere and the ADS part, and then you have some B field here in this. So this is the solution in terms of superfields, and then you plug in the action and get the action from this pure spinor formalism. So I will show the action. I'm not going to use the action anymore. It's just to show and fix some notation. So we have this algebra. No, only here I organize these generators of this algebra in terms of the Z4 automorphisms that you have T alpha alpha and T alpha dot. Then you can compute this left invariant currents, and then the action depends. It's not very complicated when written in terms of the super trace. And you have this lambda, that's the pure spinor ghost. So have two of them, and then this omega is the conjugate momentum of this pure spinor, and this it's some covariant derivatives that this pure spinor they transform under this gauge transformation here of the denominator of the coset. So I'm not going to use the action anymore, but this action basically follows from replacement of this general action. So it will be important to introduce here some notations. So I work mainly with SO notation. So these are the pure spinor constraints that I mentioned, right? And basically in the SO8 notation, you take this chiral vio spinor and decompose in a pair of two spinors, A and I dot. And using this polymatrix, this pure spinor constraints becomes just here. So this is precisely the pure spinor constraint in SO8 notation. So it will be important. I will be working with the full BRST, and you appear everywhere these combinations of lambda. And the translating this pure spinor constraints in this language, I have just a change of variables. I get the pure spinor constraints in this SO8 notation. They are quadratic constraints. They are very complicated. So this is something that a complication of the formalism, that the constraints are quadratic. But in any case, it's possible, this is in any background, to solve partially these constraints. So you see it to be important. So the way it was constructed, you can write this lambda A minus, just using this sphere identity, some manipulations, only symmetries of this matrix, and you see that you can write this lambda minus as a function of lambda plus, and then you can take this lambda plus as unconstrained variables, and the remaining, but this lambda bar is still constrained, and this satisfies this constraint. So this is a partially solving the constraint. Basically what it's saying is that this lambda plus, 8 of them, it's A, this is SO8 index, they are free, they are totally unconstrained. And then you can replace everywhere. It's in a path and not everywhere. You have to be take care that everything is defined globally. And then there is this remaining constraints here that are still unsolved. So why this will be important? Because I will use strongly the fact, in fact, Berkovits used strongly the fact that lambda plus are unconstrained variables, and you see that we can define this vertex operator in different pictures. So it's very important to notice that these lambda plus are unconstrained. So, okay, mainly the manipulations to construct the vertex operators are very complicated if you do something analytically. So basically, in the paper, most of the simplifications and everything was done numerically. So I just mention the numerics because this is well known that a pure spinner has 11 independent components. And in fact, it's possible to solve the constraint. So I just put here, starting with SO10, you can write some basis combinations of gamma matrix and write some algebra of creation and annihilation operators, and then expand this bosonic in this basis, like because it only has even B's because of the chirality. So this will expand. And then when just impose the pure spinor constraint in this language, you see that you can solve in this way, and it has 11 independent components. So this is a solution. So it's possible to generate numerics and then it's once you have the solutions. Here I'm using what is known U5. This I forgot to mention, but this I prime goes to 1 to 5. So I'm breaking basically U5 notations. But here in this work, I'm going to use SO8 notation. So basically I have to map. It's just a group theoretic map how to go to this as U5 notation to some other notations. But basically it's possible to work with this pure spinor numerically if you want to do some simplifications. Basically, everywhere we replace this lambda minus, and you have these additional constraints that you can also transform it symbolic, and the remaining still have many terms. This is some complicated. The way it was done was mainly numerically, so the construction of this vertex operator. So okay, only now it's only to fix notation, so I will be using the algebra. It's PSU224. Organizing the matrix, I'm not saying that PSU has a matrix representation, but I'm organizing this in this way. I'm showing all the generator here. So we have the usual Q and Q, that translation, special translation, that 32 supercharges. I'm not going to write Q's and S that usually appears in the PSU language. So just M are basically the Lorentz, and just the diagonal part has the dilaton, and just J. Basically, I'm treating similarly this AGS part with the SO6 part in this way. So basically, this J is some charge in some cycle of a sphere. Of course, this B is the hypercharge, but in the very end, I will drop it to get to the PSU224. So I remove it from all the commutations related in the end. And I just write the charts here if you have some index alpha dot and alpha, it appears in this way. So this slide is just to fix convention. So basically, what are my generators? And then there is the coset. So we have to select a particular representative of the coset, right? So so we picked this one. It was not totally arbitrary. You see that we have here you have 10 bosonic coordinates. You have this X and Y here, and have Z and W, and 32 fermionic components. So basically, as you see, it will be clear when I show the transformations of the coset that it's very nice when you put all the generators that you annihilate this vertex. I will be construct half BPS vertex. So they are, yeah, and I will focus on in the bottom of the supermultiplet, so that all the states are be annihilated by 24 supersymmetries. So basically, it's very, the transformations are easy and the expressions get are simpler if you put all the generators that annihilate the vertex to the left. So this was some experimental evidence, and also there are some you see it's not hard to see how they transform in this way. And then when the coset the coset, when you apply this gauge transformation, so in the infinitesimal form, it acts from the right. You have this infinitesimal transformation. So these are the generators of the gauge group that was in the denominator. And then if you act with some global passive transformation in the coset, basically you get this way how these coordinates transform. So this is the coset I'm using. And then, okay, I will just show it is not important. I just want also, because there are many notations. So basically, the BST transformation, this pure spinor formulation, it acts in this way. When you apply it to the left, it generates this expression. So you have some lambdas here that are the pure spinors. So is that combinations in SO8, and I further break down it in terms of I and alpha, just two index that goes to 1 to 2. And then there is a compensating gauge transformation, right? So there are basically two ways of dealing. We can impose, as you see, that the BST operator is nilpotent up to gauge transformation or not. So there is this compensating gauging transformation here, because when you fix a coset, you are fixing some gauge, right? And then there is this compensating gauge transformation. And I just show, for example, when try to solve this equation, this straightforward, it's not it's just a manipulation, but it's very tedious. You get that the BST transformations are very complicated. I just put one case here to show. So I have multiple commutators, have some rotation matrix that has very high order in thetas, all the thetas. And basically the pure spinor variables also transform. So why they transform? Because we are taking the BST operator to be nilpotent, acting in any field. So, and here is why is important that these lambda are pure spinor. Basically, for the BST operator to be nilpotent, it's important that the lambdas satisfies the pure spinor constraint. This is the requirement for the BST to be nilpotent, is that the lambdas are pure spinors. So here again, here I work with SO8, but I break down in this index. So again, here I wrote down the pure spinor constraint terms that that index that I'm using here, but it's the same constraint I wrote in several different notations basically. So this is the condition, the nilpotence, and this the BST is only nilpotent if the lambdas are pure spinor. So
sorry, I have some question here.
Yeah.
Previously, you said lambda is in SO8, but here they are in something like SO1 comes 3 times SO4, because otherwise it's inconsistent with global symmetry of ADS by cross S5, right?
Yeah, I don't know if you ask about the notation, so I have here in SO8.
No, I think this is the notation for SO4 cross SO4, not SO8, right?
Yeah, I'm breaking SO8 and write in terms of SO4 and SO4. Yes.
So it's kind of what to say. You are kind of gauge fix taking light cone gauge fixing delta and J, and then there's some residual symmetry, and then this lambda is already in this USB 2,2 times USB 4, or they are in this coset part only after acting on Q.
No, this is basically it's exactly the pure spinor conditions because
No, my question is what happens if I just take lambda, then lambda carries the index of USB 2,2 times USB 4, or they are living in a larger space.
Yeah, maybe I show the algebra is writing this way, right? So I'm contracting the lambdas with these alphas and i's and j's, and so they appear in this SO in terms of I bar, and I don't know if it was the question.
Then probably in the bigger space. This lambda cubed BRS.
Yeah, I can map it back. So here, if I want to map it back, I can recover the SO8 notation just via this map. So at the moment, I'm not breaking anything. So it just I'm not. You say that the vertex in a kind of light cone gauge that you talking in a bit. So it's, if it is your question.
Yeah,
but
actually,
here is basically the way I represent the algebra, right? In terms of this index.
That's right.
And then the pure spinor here are contracting the Qs. So it has some alpha and i's or some SO4, or you can say SO6 that are spinors of SO6.
So what is the meaning of this lambda Q? Lambda alpha I contracted with this Q I alpha. Does it still have some index?
Yeah, this is precisely, it's the same content. I'm not imposing any more further that the usual pure spinor constraint is the same. I'm just using that because I'm breaking the SO. Here it's writing in terms of this 10 dimension, right? So I'm just breaking this constraint in terms of SO8 or SO6 or smaller groups, but that is exactly the same. It's basically, for example, here is the same content as this 10. There is no additional constraint. It's exactly the same. Right. Basically, I think, for example, to go to SO8, I pick just via spinors and break in this way.
Yeah. This part is fine, but later you show lambda Q, the commutator.
Yeah, and then the commutators here are lambda contracting with these Qs. So it's lambda beta I or something like this. And the algebra, it's the usual.
Are you saying that these Qs are kind of this gamma matrices?
No, these Qs are.
Yeah, they're generators, not the gamma matrices.
Yeah, they're generators. Yeah.
Yes. Then the next, maybe next slides.
Next slide.
Sorry. No, then further next.
Yeah.
Okay. Then here you have lambda Q, and lambda Q have some indices.
Yeah.
Okay.
Here is this contraction.
Oh, okay.
Yeah. Sorry, there are too many index and. Okay, so now you move to the vertex operator after only this review, and I hope I have fixed some notation, but there are many. So, okay, so this talk is about supergravity vertex operator that are half BPS. So we know that strings in S5, S5 are dual to the n=4 super-Young mules. And if you take about half BPS operators in super-Young mules, they have this form. So all the half BPS operators have this form, where Y here are some non-vector, right? 6-dimensional non-vector is this phi hat. Here are the 6 scalars of n=4, and this L is basically the length of the operator, and x tilde will be some position. And then you can put these operators. I construct vertex operators that are dual to very specific polarization, very specific half BPS. You can always rotate, apply SO6 notation or FSO6 rotation, pass U224 to get more general expression. But then you can fix this Y bar in some particular orientation and take an operator, right? I can take a particular vector, and then I can take this operator to satisfy this J will be the charge along. You can think maybe of Z and Z bars, that Z it has positive J charge and Z bar has negative J charge. Will be some operators. So basically, I take this operator, select a particular polarization, they satisfy this condition, and also they are annihilated by 24 SUSIs, or you say like 16 S, special conformal transformation, plus 8 SUSI. So this is the dual operators, and basically I'm going to construct vertex operator dual to these operators. So this, in the picture -8, this was done by Berkowitz. So what is the vertex operator in the picture -8? Basically, it's very simple. It's a very simple expression. I can write here in just a few lines, but then I will explain the expression. So basically, it's the following. So basically, you have these deltas, these delta functions, and the way it's interpreted is via bosonization. So you remember that when you partially solve the constraint, this lambda plus can be taken as independent components. So you have some 8 independent lambda plus and 8 independent conjugate momenta. And then you can use the traditional data bosonization to define this operator delta here. And the picture of the vertex will be the number of deltas. So basically you have 8 deltas here. So you have a picture -8, right? And then there is also a prescription to move pictures. So basically you have to apply this is the operation. If you want to go to the picture -8 to the picture -7, you apply this operator that when it acts in the deltas, it goes to the denominator, and then you apply the BST. So this was the like a conjecture, like this was proposed by Berkowitz, that this is the picture -8 vertex. So it depends in 8 theta's, because it has annihilated by 24 supersymmetries, so it can depend on 8 theta's. And it only depends on particular, in a few lambdas, not in all of them. So they depend only in just particular combinations of lambda. So you can say that's some kind of light cone gauge. And this N and Z, basically Z will be the distance to the boundary, and this omega will be the R charge. So basically, if you want to relate this to the dual operators, you have to take this N equals to -L. So this will give you basically the dimension and basically the R charge of the state. So this was the idea of Berkowitz. He proposed this picture -8. And basically there is this procedure to move the pictures, right? And one way to get the vertex is to apply 8 picture hazing operators and eliminate all deltas. So a nice question to ask is if this picture -8, that's super simple, if they work in any background, or it's just very particular to ADS5, S5. So I don't know the precise answer for which backgrounds we can have some very nice expression. There is also the question if we can compute things with this picture -8 vertex, for example, if you want to compute some amplitude or something. So I think this is some open question, because it's a very simple expression for the vertex. And it's important, what's the properties of the vertex? So what's the properties of the vertex? First, we can compute the PS2 transformations of the worldsheet variables. So we have this formula, you act with any generators here from the left and get the transformations of the worldsheet variables, right? And there is some compensation gauge transformation that will rotate the lambdas transformed via gauge transformation. And if you compute this transformation for all the generators, I put here some of the transformations that are relevant. You see that the vertex it's is killed by 24 supersymmetry and also by Q and Q. So it has the same properties of the duals. And it's BST invariant. So this is important. So it's BST invariant. So it's a good state. That is the question if it is always the question when you compute vertex operators, if it has to be close but cannot be exact. So I will say that it's not exact in the zero picture form. So it would be nice in flat space. In flat space, in fact, it's possible here. I will focus only in the bottom multiplet. So this is the expression for the bottom multiplet. So you can, of course, get all the states of the multiplet by acting with supersymmetry. But in flat space, it's very nice that you can write it in terms of superfields. So that is the superfield that appears in Green-Schwarz and Brink that has this constrained superfield and has all the fields of type 2B supergravity. And basically, it's very compact. This is flat space. You can put the field here and you get the full multiplet. So it was argued that by Haslop and Howe that in fact, in ADS, if you take first order fluctuations, you can have the same superfield. So maybe in ADS, it's possible to super covariantize the vertex in terms of these phi's. So it's something that we haven't done. We just compute the bottom component, but maybe it's possible to write in terms of covariant derivatives and superfield, all the full super multiplet. So, okay, I put the answer. It's very complicated, but I make some comments why I put. So first, the theta's that appear here, it has expansion in theta's. So this is when you apply 8 picture hazing operators. So when you do this, you generate a huge amount of terms. So it's computation in terms of computation time. It's very hard. And many of the simplifications that you get this zero picture vertex was done numerically. But in the very end, one way also to compute the zero picture vertex is write all the invariants. You see that I have all the invariants here that are allowed by the supersymmetry and basically solve the cohomology numerically. So this is something that I perform some tests. Instead of going to my picture -8 to 0, we can start to write some invariants and try to solve this cohomology numerically. Why numerically? Because the complications with the pure spinor constraints are that they are quadratic and super hard to do some manipulations analytically. So numerically is very helpful. So the vertex has 5 terms, right? It has terms with 2 theta's, 4 theta's, 6 theta's, and 8 theta's. The theta's that appear, I remove the tilde, but the theta's that appears are dischargeless theta's. So they don't care conformal dimension or are charged. So the vertex has well-defined conformal dimension and not charge. And then the nice thing that appear here is basically it's if you take all the terms. So an important comment you have these combinations of Pauli matrix 1, 2, 3, 4 that basically it's because of this Ramon flux that breaks. It's not the vertex is not SO8 invariant. So you have this term. And the nice thing is that you take for all the terms here, the maximum power of n. This is precisely the flat space vertex. And basically you can think of ADS as some flat space plus some corrections here. So you have this additional correction basically proportional to sigma 1, 2, 3, 4. that is basically breaking this SO8 symmetry that you have in flat space. And so this is the comment. If you take, in fact, if you take the flat space limit, you have to kill all the terms of is lower n. So I just put the expression only to make a comment that all the theta's are chargeless. You have this term that breaks SO8, and basically all the terms of bigger n are flat space. So it has a very nice and simple flat space limit. So okay, so we can say that it's a kind of light cone gauge because the expectation was that the vertex would depend in all the lambdas, but in fact it depends only in these lambda bars here. So they depend in less lambda bars and depend also in less thetas, this bottom component. If you go to higher components of the multiplet, you get more thetas. Basically, you take our vertex and act with SUSY. If you act with supersymmetry, you get all the states of the supermultiplet. So it should be possible to recover a more general, more covariant description in terms of all the lambdas, basically by adding some BST trivial quantities that does not change, basically changing the vertex of the gauge of this vertex operator. So the vertex is always defined up some BST trivial quantity. So if you start with our vertex that only depend in lambda bars, we can start to have, as I show in the next slide, you can have dependence on the other lambdas only by adding trivial BST trivial quantities. So, okay, so one comment is the dilaton. So one test of the vertex, it's what happens when n equals 0. So this vertex is well known. It was constructed by Bertukovitz, is the dilaton vertex operator. This dilaton vertex operator in integrate form is basically the Lagrangian, is the Lagrangian of the pure-spinor Lagrangian that the action that I showed in the beginning. So this is an unintegrated vertex of the Lagrangian. And if you take our vertex and sum these BST trivial quantities, basically do a gauge transformation, you see that we recovering our notation this dilaton. This dilaton, this vertex operator, basically it changes the radius, the model of the radius of AGS. So it is because the action is PSU 224 invariant. So this dilaton is manifest PSU 224 invariant. So this was one test. This dilaton is present in NDS, but when you go to the flat space, it becomes trivial. It's not in flat space because it's a moduli of that disappears when you take the flat space limit. So this was one test of the vertex. The other test was the correct flat space limit. The flat space limit that was done in the paper, you can understand to start with the algebra PSU224 /4, and then you basically deform this algebra continuously to the super Poincare algebra. And also in this way, you can also think about this flat space limit that maybe it's clear at this point is in terms of BST transformations. So basically in the flat space limit, your BST has to become the flat space BST, right? So the BST transformation of the variables in ADS are basically flat plus a lot of corrections, higher order in thetas. So when you take this flat space limit, basically the BST recover the flat space BST. And as I mentioned, in this flat space, we kill several terms because basically you take this lambda, I'm doing this scaling with lambda, and then you take this lambda to 0 and you kill several terms that have with positive powers of lambda, and you recover the flat space limit. There are many ways, I think, to take the flat space limit. I think this is not a unique way, but basically just it's a precise map here. It's very, very, very precise. So just mention a few words about the boundary. So in our coordinates, how you compute how you understand this ADS S5 geometry. So one exercise to set all the fermions to 0, and then you get some two cosets parameterize basically ADS and S5. And then if you take all the fermions to 0, we get this expression in our coset. And then you can use some matrix representation to write them in this way. And basically you can define this gauge invariant. So remember this matrix acting from the right here will be gauge transformation. You can define some gauge invariant coordinates that satisfies the ADS and the S5. So this is the geometry. And it's also possible to do the usual way to compute not usual way, but the standard way is to compute the Vibing of the Fubine of the coset, right? And then contract and compute the metric, and then you get this metric in ADS. So this in our coordinates is very similar to the usual Poincare coordinates, but you see that is not exactly the same because you use K here instead of P's. So there are the Poincare coordinates. In the Poincare coordinates, you have the P's. So the X has the correct conformal, has the right dimensions, right? And you can map these two kind of our coordinates to Poincare coordinates, and in the boundary is just the inversion. So this is basically the inversion. And there are more possibilities. You can parameterize, you can have some global parameterization of ADS, and not because the Poincare covers some, not the full thing, and our coordinates not the full, but it's possible to do some global, use some global coordinates, but the computationally is very complicated. It'll be very nice to use just global coordinates because then you can do translations and move this vertex more easily, but it's a bit hard. So computationally to compute the transformations are very complicated. So okay, so if you go to the boundary, you can analyze the metric. You see that the boundary is it's a z equal infinity here. And there are two possibilities that maybe are discussed more in this paper by Heslop and Hoey. So there are some cosets that it's very consistent to put 16 of the 32 thetas to 0 at the boundary, to set them equals to 0, because the transformations of the book does not change the values of these fields. Or it sometimes, for example, for our coset, it's not consistent to set any theta equals to 0. But then you have that the vertex operator has to depend in when you approach the boundary, it has to depend in the lower number of thetas. So basically our coset is the second case that when you approach the boundary. Here, because this vertex is it's only dependent on 8 thetas. So in there it is the 8 thetas. So when approach the boundary, you don't have just 32 thetas, only 8. So there are just two possibilities. And then you mentioned the conclusion. I'll say more, I think, many words about the conclusion and open problems. So, okay, so one big motivation is to compute the amplitude. So this is some work in progress with doing with Lucas, Luis, and Alday, and also Tobias. So we are trying to compute these amplitudes. So the pure spinor, it's not does not have a complete geometric understanding. So usually the prescription is something that is not so easy to find. So in flat space, how it works, basically you have to saturate. So okay, so to compute the prescription, you have these vertex operators. So first we compute the vertex operator in a very specific point. I forgot to mention, but it's the dual operator. It's annihilated by K only when you put it at the origin. So we compute the vertex operator in a very particular polarization and position. So first, to get some non-zero amplitude, you need to rotate this vertex operator, right? To write some PSU 224 transformation, to put different orientations to get something non-zero. So this is so it's possible using this result to get more general expressions. And then in flat space, the prescription was one way of derive the prescription is to add the so-called non-minimal pure spinor variables. And then it's possible to show that for closed strings, you multiply these three vertex and get, you have to read some specific combinations of thetas and lambdas. So in ADS, basically it's not super clear how to do the prescription, but there are many approaches. You can do some brute force or try to see how to compute it. So this is something that is still open, how to compute the prescription, and in fact get the amplitudes. And also I mentioned the unintegrated vertex operator. So it's possible to compute, if you want to compute more than 3 points, you need the integrated ones. So the integrated ones has a lot of literature about them. So once you know the unintegrate, you can compute the integrate. So there are some papers by Breno and Shendia and Mikhailov that you can get some results from them. Basically, they have the results in terms of superfields. So we can try to read them. But even the 3-point function will be nice. So you know that it's protected and you know its expression will be not a new result. Even all is not there are many things that we can compare. So there are many safety predictions of the amplitudes. So okay, so there are also something that it's very, because these numeric techniques and these pictures maybe can work in other backgrounds, not only just 5S5. So maybe it's possible to do more in a general background, also try to write in terms of some superfields. And at the moment, I only know how to do the theta expansions for coset space, super cosets, to do just that expansion of the superfield. But it should be possible to do in general case, but I don't know how to do. So okay, it would be nice to focus in other theories. And also it will be very nice in flat space. There are recent and many nice projects about the massive vertex. So here is only half BPS, and basically the half BPS, the nice things about them is that they do not depend on alpha prime, right? So basically there is no alpha prime. But once you go to massive ones, they have, the masses are very complicated functions of alpha prime. So it would be very nice, for example, to take a PE of the vertex, or use, for example, there are some techniques by Renan that he constructs some specific operators in Lipinski-Zuzinskas that he computes some in flat space. He has some operators that we can maybe try to generalize to apply using the massless and get the massive vertex. And it would be nice because to compute there is some prediction for the spectrum via integrability. And of course, you'll be, if you want to compute the amplitudes, it'll be necessary to compute the OPEs of the fields. If you want to compute the expansion in terms of the corrections, right? Not only, and it's possible. So in pure spinor, it's possible to compute these corrections of a prime corrections. It's complicated because you have one way of doing it's brute force. Basically, you do all the Feynman graphs and get these corrections of the OPEs. But I think here is be very nice to use like bootstrap methods that and related with other results or the techniques, and also it would be very nice if we could at least reproduce any result, no result, and make connections with integrability or other techniques. But here, for example, the current algebra, the OP of the current algebra was used already, for example, to compute some spectrum, some masses. So it would be very nice if we could do this, the algebra of currents that appear in the action. If we can compute this algebra at the quantum level, it's not known what is it at the quantum level. There are many progress in the not the full algebra is not known, but there are some intermediate some pieces of the results in the literature. But it would be nice to connect with integrability and other techniques like bootstrap and yeah, I'm expecting that it's possible to learn about GSOP via bootstrap, to set some bootstrap program and try to compute that. Okay, so thank you very much. I have to thank also the Serra Pilheira that has financial support of this and other works. So thank you very much for your attention.
Yeah, thank you very much. Anyone has some questions?
Yeah, maybe I have a question, Thiago.
Yeah, yes, please.
So in the so is it feasible to compute like 4-point amplitudes with this vertex, or is still very complicated? Because I mean, I guess that a lot of the pure spinor goes into some kinematics of the 4-point amplitude, but then maybe the dynamical part you can get a guess for what kind of integrals you have, right? I mean, if I think about the flat space analog, like in Virasoro-Shapiro, there is a lot of business with the spinors to get the kinematic polynomial at the beginning, but then the gamma function integral is simple, like, and then the dynamics you understand a little bit. So is there something along this line, or very, very naive?
Yeah, so yeah, this is my personal great motivation, is to compute these amplitudes. And okay, so here we have the unintegrated vertex operator. So I mentioned the steps. So to do the 4, we need also the integrated ones. So this is not super complicated, because if you act with some BST in the integrate, you have the unintegrate. So there is this map already in the literature how to go from to. So in terms of the vertex, you can get the other one. So also here we are a specific polarization and specific position. So there is something that it seems it's algebraic, but it's a bit it's
right,
very
yeah,
hard computationally to rotate this vertex to different points. So you have to put some orientation that you get a non-zero zero amplitude. Okay, it's okay. So this is the first step, and then the last step is basically the prescription. So if you know the prescription, you can fix the prescription with the 3-point function. So once you know the 3-point function, for compute the 3-point function, then you can compute basically not only 4, but we can write any vertex operators here, and the prescription will be the same. And then it's needed is the OPE of the fields. You have the action, right? Then you have to compute basically when you start to have just integrate vertex operator, you have to take the OPEs of these fields. So basically the missing part that we are trying, and many Berkovitz has some proposals, and it's basically also we are trying many things. So it's also fixing this prescription. But once you fix, I think there is no restriction. You can try to write 4 or 5. It will be the final expression will be complicated, but at least we can compute is take the OPs of the fields, and then computationally, I don't think it will be very. The vertex is not much more complicated than the flat one. It's just some corrections.
right.
It'll be. So once all these ingredients are fixed, we can try. It's possible to move to at least to try to compute 4, 5, and also 6. And
I see.
but yeah, so
So,
Yeah,
but this
this-
prescription that you mentioned has to do with, in particular, with, I mean, what kind of aspect is going to cure this prescription? The zero modes or extra?
Yeah, it's
kinematic?
basically the zero modes of the worksheet. So you have
I
the
see.
zero modes of the thetas, the zero modes of the gammas, the pure spinner. So because the pure spinner does not have a very clear geometric interpretation, it's not so clear how to compute the prescription.
I see.
So usually you start with the path integral and put some regulator, and this regulator, and then you see how to deal with the zero modes. Basically, the properties of the prescription, it has to be BST invariant. That this is very strong. So it is also.
I see.
Important. But yeah, yeah, I don't know. It's we are trying. So, and, yeah, this
Okay,
is the
cool.
missing building block. It's just this prescription. And also, okay, the computation is not. It's very long and it's computer. You have to take some computer time. It's many terms, but this is okay. I think this is from the technical side, but from the. Yeah, but once you have the prescription, it's only necessary the 3 points to fix the prescription. And then if you have
I
these
see.
3 points, and then you can go to any higher point. It will be the same prescription. The expression will be, it will be very complicated, but it's to take a piece of the fields and
Yeah.
you can take try to compute corrections and.
But you have no guess for what kind of dynamics is going to change compared to flat space, or do you have a guess?
No, at the moment, no.
Okay.
It's really a work in progress.
I mean, like even for the vertex in which you have this extra dependence on the charge, right? With these polynomials. This
Yes.
was, were you expecting the polynomials to have maximal some degree, or that was totally new for you?
Yeah, the degree we were expecting, because it cannot have, because this n polynomial n, you can think it's basically, it appears in the exponential, multiplies the worksheet variables, so it's like momentum.
Yes. Yeah.
So we know that when you take the flat space limit, it's necessary to have a non-singular value.
Right.
It's not possible to have arbitrary powers of n. So,
I see.
So the power of n is, we had some expectation of the maximum power, because it depends on 8 thetas in the maximum, in the bottom. You're talking about the bottom, that's annihilated by 24 SUSY. So then, yes, we had some expectation. But for example, something that I had some discussion with Lucas, because if you see, there are some prime numbers, 37 and something very 19, some numbers. The corrections are very, very, very nice numbers. So I don't know.
Yeah.
We still do not know the meaning of this, but it's very. But yes, the power of n, it cannot be arbitrary. It has to stop if you stop the number of thetas. Otherwise, the flat space limit is lost. So
like the first correction beyond flat space, if you do an upgrade of the Heslop-Howe prescription with the, I guess you mentioned at a certain point in the slide you had an operator acting on a superfield. If you covariantize that operator, maybe you can get the first.
Yeah, this is what was the difficult here. For example, here, if I take I'm showing the picture -8 vertex, right? It has 8 thetas. So to covariantize the flat space one, basically you change these 8 thetas by covariant derivatives and put a superfield here. So this is possible because the algebra of the covariant derivatives are very simple in flat space. But then when you have in ADS, when it's not only changing the thetas by covariant derivatives. You have to do this and add more terms.
I see.
So it's something that it would be nice to have it, but we don't know. It's how to. There is also a question that Berkowitz point out to us that maybe if you here in the flat, it only depends on just 8 lambdas. Maybe in ADS, the other states are going to depend on more lambdas. So there are something to understand here, how to covariantize the ADS vertex. But there is the brute force way, starting with the bottom and acting with SUSY, you get everything. You get all the states. So,
I see.
but it would be nice to write very compactly in terms of superfield. In terms of a superfield. But just we don't know how to do yet.
I see. Thanks. Thanks.
Thank you for the question.
Well, I have some questions. Can you think about the opposite limit? Like, I guess your result is alpha prime exact. Then how about tensionless limit?
Yeah, this was. You mean the age is going to 0, right?
Right. Huh?
So yeah. So this is. This was done in the pure spinor formalism, like at the same, also by Berkowitz, like in the same. It's the title of the paper is trashing the proof of Maldasena's conject is I forgot the precise title, but it's the same. It's the same. It's almost the same month that appears half PPS separate. When you take this limit R goes to 0, the pure spinor action simplifies enormous. So it's basically a BST trivial quantity. And then you can use like, it becomes like a topological action.
Mm-hmm.
And he proved that it's equivalent to 3 Young Mills.
Mm-hmm.
So he had this 3 Young Mills. And he mentioned that he can write the interactions. He gave like a heuristic argument how to correct to get the interacting super Young Mills. But this was done by him. So he took this limit and basically it becomes a topological string. And then you can compute things via topological methods. And that is also now this different way by Gabardia and Gopakumar that they have these twisters and small radius. But the pure spinor, it's done. It's done in this paper by Berkowitz.
Does your vertex operator simplify in this limit?
Limit. Yeah, in this limit, what is simple, it's also the massive vertex ones, right? Because this has like a free string, but our vertex, yeah, I don't know precisely the expression will be or something. If you want to.
I see. I have a very basic question. Because in RNS formalism, the reason it doesn't work is somehow these pictures are not somehow compatible with the Walsh superconformal symmetry, and then you have to enlarge the Hilbert space and so on and so forth. But the reason your computation works well is that you can construct somehow the DRC exact quantity in the pure spinor, and then it guarantees Walsh superconformal symmetry. Is it correct?
Yeah, it's the action is in.
No, you don't have to extend the Hilbert space when you say pictures?
No. Here it's the pure spinor it's well defined in any background Hammond flux, and there is no difficulty. It's just it's the same. If this is in fact yes, the Hammond-Nevo-Schwarz, when you act this Hammond vertex operator has half integer picture, so there is this problem how to deform the action. Also, there is some branch cuts, and there is all this. But there are some progress that people try to write Hammond flux. But in pure spinor, there is no it works for any background. So you can put Hammond, and there is no one. The vertex operators are more complicated here because usually the vertex operator in pure spinors were computed when without Hammond flux. You have this factorization and left and right. So it was the product of left and right vertex operator. In flat space, it was constructed in the way. You take the open superstring vertex operator, multiply the left and right, and get the closed one. But here, because you have Hammond, there is no factorization, right? So there is no in holomorphic and dimensional. If you take this current algebra, it's not holomorphic, or it's. So this is some difficult. The vertex operator need new techniques because you don't have this factorization. But there is no difficulty in pure spinor to do any kind of background. You just plug the background solution in the action, and you get the action, the BST transformations, and always the quantization. The vertex operators are states with ghost number 2 in the cohomology of the BST operator. So
I see. Okay, coming back to this question of alpha prime exactness, there is this localization results about integrated 4-point functions. Also, there's results about flat space limit, but I guess the results are very complicated, like involving many transcendental functions. And in your computation, if you want to reproduce transcendental function, you have to sum over something. Typically you need some infinite sum to get transcendental numbers.
yes.
Is there any reason to get this sum from some prescriptions? It's just like OPE, for instance.
Yes,
I guess.
Okay. Oh, sorry.
So I was saying that perhaps in the case of the 4-point correlator in which you get these transcendental numbers, he still has to do an integral, right? When he has reduced, that integral might be interesting. But... I mean, there are two possibilities. Either it comes from some prescription about the zero modes that puts in some transcendental stuff, or the prescription of the zero mode somehow does do much, get some number in front, and then the integral is left with is, I mean, in the second case, if the integral is carrying all the dynamics compared to the zero modes, then I guess the integral is very nice to guess what it is, but I don't know. But probably Thiago knows better there.
No, yeah, I mean, there are many things to do. I mean, if we could start to compute the amplitudes, I think it's not clear at this point.
Okay.
Yeah.
Any other questions? If not, we thank speaker again.
Okay, thank you. Thank you very much.
Thanks a lot. Thank